Hi there, this is Space Nuts, where we talk astronomy and space science. And my name is Andrew Dunkley, your host. It's good to have your company. On this episode, we're going to Mars, where we're going to talk about water. Now, water is a very common Martian topic, but this story is going to throw a completely different light on Mars water, and we'll tell you why. There's also a great idea that's being put forward to help spacecraft re-enter Earth's atmosphere, because up until now we've used heat shields and tiles. Now they think they've come up with something completely different. It's called sweat. And the universe, RIP. Yep, we're going to see it all end much sooner than we expected. We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again for more. It is Professor Fred Watson, astronomer at large. Hello, Fred.
Andrew, how are you doing?
I'm doing quite well, thank you very much. Are you?
What a surprise to see you. Yeah, I'm very well, thank you. Yeah,
it is a surprise to see you,
no
there, I mean. Yes. Do you like my new background? I'm going to change the background every week on my studio.
I think that's a good idea, and I do like it. Actually, it's a place that's close to my heart as well as yours. It's a great place. Isn't that the saying? You know, I left my heart in San Francisco. Yeah, you probably did.
Yeah, so I left my. That's a photo I took after we crossed the Golden Gate Bridge, looking back to San Francisco. So I thought I'd use that as my backdrop today.
The second line of that song's a good one as well. I left my knees in old Peru, courtesy of the goons.
Yes, of course. Yeah, beautiful city, really beautiful city. I think I told you about the driverless taxis they've got, but there's so much more going for it. Those cable cars are fantastic. We obviously did the tourist thing and did a ride on one of those, and then did the walk down Lombard Street, that zigzaggy street that has become quite famous, and I don't know how many movies and TV shows it's been in, but and it's like all of these things that when you see them on TV, you think, oh wow, got to go see that, and then you get there and go, oh, it's a lot smaller than I thought. But yeah. I don't know what the price of a house is on Lombard Street, but it's beautiful homes there.
Yes.
But overall, a beautiful city. Beautiful city. I'd go back there tomorrow. We better get into it, Fred. And our first topic today is the water on Mars, or in this case, according to a new theory, inside Mars. And we're talking about massive amounts of water.
Indeed, that's right. We are. It's not just a few drips or drops. So the story, the star of the story, Andrew, is NASA's InSight spacecraft, which it's more than a decade ago now. I think that InSight landed. You might remember it landed in the Arctic region of Mars, and basically did one summer's worth of work, because we knew that once it got into winter on Mars, the spacecraft would freeze and all the electronics would die and it would pass away, which it did. It's still there, of course, but it's inactive. So a great mission. It had one little hiccup in that the thermometer that they were trying to dig into the ground didn't get dug in. You might remember. Right. We covered that on Space Nuts. But what worked a treat was the seismometer, because it had a very sensitive seismometer able to listen to Mars quakes. And Mars quakes are caused by a number of things. Impacting meteorites actually cause a little quake. And they also think there's some residual, not exactly plate tectonics, but just slips and slides of fault lines and things of that sort, which also create seismic data.
Yeah.
And so this is where the story really starts, because we know from other evidence that Mars, probably between about 4.1 and 3 billion years ago, was warm and wet. The evidence is in your face in many ways. You can see evidence of beaches and river channels, and the northern hemisphere of Mars is much smoother and flatter than the southern hemisphere, which we think is because there was possibly an ocean there. So all the evidence is that during that early period in Mars's history, and just remember that all the planets are 4.6 billion years old, or thereabouts, 4.7, something like that. 4.1 billion years is only 500 million years after the origin of Mars, but we think that was more or less the start of when it was a warm and wet world, and that lasted for nearly 1 billion years, a little bit more perhaps. So the atmosphere, the water on Mars is now no longer on the surface. And that's pretty evident because it's as dry as dust. And in fact, it's got a humidity effectively, not quite, but effectively of zero, very, very low humidity. So the questions have always been, where did the surface water go? We know that because Mars does not have a strong magnetic field, it's bombarded intensely by the solar wind, and that tends to separate any water vapor into its component atoms, hydrogen and oxygen, and that they then basically waft off into space. And we know that's happening because there's a spacecraft called Maven, which is still active in orbit around Mars, and that can see this stuff all leaking away. So we know that was part of the story. But the planetary scientists who look at Mars in detail say that's not enough. We can't actually account for all the water that must have been there by it just disappearing into space. We know some of it's frozen in the polar caps of Mars, and probably, hydrolyzed minerals, that they've been minerals on Mars's surface have been affected by water. That's still the case. However, there must be more. And there was a calculation done, I think, by the research group that's done this work with the InSight lander, which estimates that the water that's gone missing was enough to cover the planet in an ocean between 700 and 900 meters deep.
Yeah, so that just blows me away.
Yeah. It's gone. And that's not an insignificant amount of water. Remember, Mars is only half the diameter of Earth, so it's not like an earthly amount, but it's a lot of water, 700 to 900 meters deep across the whole planet. So where's it gone? And if we can find it, what might it be like? So now enter InSight. And actually, I was wrong. It's not a decade ago. It was 2018 when InSight landed and did all that super work with its sensitive seismometer. These scientists looked at the vibrations that come from any sort of Marsquake caused by, as I mentioned before, either slippage in the rock or a meteorite. But you can look very accurately at essentially the types of waves that you're getting, because there are pressure waves and shear waves. I think they're called S waves and P waves in the jargon of seismometry. But these waves, seismographic waves, tell you something about the material that they are passing through. And that is where this story has gone, because these scientists estimate what they call a significant underground anomaly exists in a layer between 5.5 and 8 kilometers below the surface, because they find that these shear waves move more slowly in that region. And the most likely explanation, and remember that's a layer that's, it's 2.5 kilometers thick. That layer, they think, is likely to be porous rock, like we've got here on planet Earth, filled with liquid water, just a little bit like the aquifers. And we've got a great one here in Australia, the Great Artesian Basin, which is...
I'm sitting on it, right?
You're sitting on it, that's right, you are. Are your feet wet, Andrew? Or
No, luckily we do have, as you know, several bores all over the city here, because we can tap the Great Artesian Basin and get that water for domestic use. So we kind of take water from that source as well as from the local river. The river is fed by a huge dam upstream, which is bigger than Sydney Harbour. And yes, that's right, Burrendong Dam. So, we definitely use the aquifer water from the Great Artesian Basin to supplement the city supply. We are actually drought-proof as a consequence of that. We will never run out of water because we sit on the Great Artesian Basin, which basically stretches north to south across the entire continent down this sort of central eastern section.
That's correct, yeah.
Yeah, it's massive.
It is.
It's like an underground ocean, basically, and that's what we're talking about with Mars.
That's exactly right. And so it's a really nice, connection that we have here in Eastern Australia with Mars. This sort of, it's almost, the rock itself is sponge-like in the sense that it holds the water, the liquid water. Yeah. And the thinking is that because it's at a depth, as I said, a few kilometres, between 5.5 and 8 kilometres, the temperature there is warmer than it is on the surface by quite a long way because of just the internal heat of the planet. And so they think it is actually liquid. And that fits the bill in terms of the seismic waves that they've detected, that you've actually got this liquid water in porous rock. And what's really nice about this story is that if that is a global layer of rock, and it may well be, they calculate how much water is in it. And sure enough, it's enough to cover Mars in a global ocean between, the figures they quote is between 520 and 780 meters deep. Just about the same as what they think is the missing water mass on Mars. So this
makes sense. Yeah. I mean, this is still a maybe, not a definite, but the numbers certainly support it. That's what's really interesting about this story. Excuse me. And the question is, if we go to Mars, and I know you don't like this, but they will probably establish colonies there if one man has his way. Will they be able to access it? Could it actually hold microbial life, and could you drink it?
Yes, that's right. I mean, the middle question there, the fact that there might be life in it, that's the one that's so intriguing. I suspect at that depth, you'd struggle to get it. But we do know, and again, this comes from InSight. No, it wasn't InSight, was it? It was Phoenix. Yes, Phoenix was a spacecraft like InSight, which was actually the one that was in the Arctic. So I beg your pardon, I said something incorrect before, that InSight was in the Arctic, Martian Arctic, but it wasn't. It was Phoenix. Two spacecraft which was very similar. One was for seismometry. InSight was basically giving us sight of the inside of Mars. And Phoenix was all about basically sampling the surface rock. You remember those classic pictures? They scraped away the top layer of soil,
and there was ice.
And there's ice underneath it. Yeah.
It was like a kid had been up there with his Tonka tractor, and he'd scraped the top of the dirt, and it turned white.
It turned white. That's right. So that is in the Arctic region, but that's telling you there's a permafrost of water, and there is a huge amount there as well. But to find liquid water now, whether that's drinkable, probably if you purify it, it might have minerals in it that you'd like to get rid of. But I think it will be drinkable. But yes, the intriguing thing is, as you said, is whether it could harbour Martian biology. That's really, really interesting. And in that regard, we've talked about the planetary protection rules before, and how much of spacecraft has to be sterilized before it's sent to Mars if it's going anywhere where liquid water could exist.
Yes.
What it would do, this would mean that we would have to be doubly careful, sort of no matter where you're going on Mars, because deep under the surface there might well be Martian microbes that wouldn't like earthly microbes if they found their way down through the rocks. So
absolutely. And we've got evidence on Earth of that kind of contamination when, like, the Spanish went to South America, and the South American people were exposed to diseases that just didn't exist in there.
Wiped them out
almost completely.
Similar things happened in our own country, Andrew, as well.
Yep,
yes,
absolutely.
Smallpox and things like that. And I should, just talking about our country, I should mention that some of this work has been carried out by Australian investigators at the Australian National University, as well as scientists at the Chinese Academy of Sciences.
Well, hopefully there'll be some follow-up to maybe confirm what they think. As I said, the numbers are stacking up in that favour. And it will mean that if that's true, Mars is not a dry, dead planet. It's probably a water world, but a different kind of water. And we're seeing more and more of that throughout the solar system.
We are indeed. That's right.
Very exciting indeed. All right, if you'd like to read up on that, you can see that at the conversation.com website. This is Space Nuts. Andrew Dunkley with Professor Fred Watson. Let's take a little break from the show to tell you about our sponsor, Insta360. I'm going to tell you about their new camera. Just keep in mind, as a Space Nuts listener, there's a special offer for you, and we'll tell you about that in a little while. But Insta360's new camera is very exciting. It's their new flagship 360-degree camera, and it does exactly what it sounds like it does. It can take footage in 360 degrees. All you have to do is push record and it'll do the rest. And it does it in 8K. And they've also enhanced the low light performance, so you'll get outstanding images day or night. If you're a thrill seeker and you love to jump off cliffs and you want a good camera to do that, this will do it for you. If you like to go deep sea diving, you can do that with this camera. If you just want to take a great camera on holidays, it'll do that brilliantly. And it's just taking night shooting to a whole new level as well. Now, with 360-degree video capture, you can get everything around you just by hitting record, find your focus, choose the best angles later with their AI technology. They've got an AI-powered reframing tool, and you do it all through the Insta360 app. It couldn't be more simple. They have built a really tough camera, and it's got replaceable lenses. So if you bung something up, they can, just get a new lens. It'll take some work to break, though, because it's got very, very tough optical glass. They describe it as a superior drop resistance, and plenty more as well. Now, if you would like to get one of these cameras, they're offering a special deal for Space Nuts listeners. The first 30 purchases will get a free 114 centimetre invisible selfie stick worth around $25 US. That's with your Insta360 X5 standard package purchase. All you have to do is head to store.insta360.com and use the promo code SpaceNuts. Very important. Store.insta360.com and use the promo code SpaceNuts. And that deal with the invisible selfie stick available for the first 30 standard package purchases only. And if you want more information, check out our show notes. But just remember the URL store.insta360.com and the promo code SpaceNuts. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Speaking of water, well, not quite, but we've seen over the entire space race to date, which began way back in the middle of the last century, that if you wanted to get a spacecraft back into the atmosphere, you had to be prepared for it to potentially burn up unless you put a heat shield on it, and later those heat-absorbent tiles that were made famous by the space shuttle. And my son has actually got one of those tiles at his place because he got it as a secret Santa through one of the social media websites when they used to do that. And the warning came, do not lick the tile. Apparently it's very toxic. So that's how it's been done to date. But now they've come up with a new idea that basically involves spacecraft sweating to stay cool as they come back into the atmosphere. This is really fascinating.
It's extraordinary, yeah. And what you've said is absolutely right. The traditional heat shield is called an ablative shield because it ablates, the heat takes it away, and that means that you only use them once. So That's an issue, for example, with the Orion capsule, which is going to be reused. This is the one that will take astronauts to the moon. It's a pretty large piece of kit. And every time you reuse it, you've got to replace that ablative shield that's on or ablative shield, however you pronounce it. It's on the back of the spacecraft. That's the bit that burns away as the spacecraft re-enters. Could you find a way of doing this which was essentially reusable, something else that would actually protect the spacecraft from the intense heat of re-entry? And it's a team at Texas A&M University, partnering with a private concern called Canopy Aerospace, and they've basically developed a 3D printed substance that releases gas when you've got the heat of re-entry. And the reason that's interesting is that gas has a very low conductivity of heat, unlike a piece of metal or something like that, which conducts heat very, very well. Gas is pretty poor at conducting heat. And it's actually why, you've got a lot of, why putting air in the space between your inner and outside walls provides a bit of heat insulation and things of that sort. It's a good heat insulator. So if you can make something that will release gas as it enters the space, as the spacecraft enters the atmosphere, then you might well find that you've got a situation where you've got something that's effectively reusable and that you don't have to replace every time. And the material itself it's a 3D printed silicon carbide, and it is strong. And I'm quoting here from the space.com article about this, which is a very nice description, written by Samantha Mathewson a few days ago or a day or so ago. It's designed to be strong enough to withstand extreme atmospheric pressures, yet poor enough for the coolant to sweat through. And she says prototypes are being tested at the university to evaluate the material's ability to sweat and how well the gas that is released insulates a spacecraft. So it is, yeah. It's a really interesting step. It's what struck me about this is we've been using these ablative shields since, the Mercury capsule back in 1960, whenever it was, 62, I think, Mercury, maybe 63, and they're still being used. They're still on the Orion capsule, which is just a giant version of Mercury in some ways. And it's great to see people thinking outside the box as to whether we can find better ways to do this and actually create new materials, given where we've got to today in things like 3D printing, create new materials that can do the job better.
Yeah, I suppose the only way to really test this would be to create this new form of shielding and send one up and bring it back and see if it survives, basically. And you wouldn't want to sort of go up there unchecked and go, okay, we're going to test this new.
No, you wouldn't want that. They've used hypersonic wind tunnels to test it. And these are things that blow the wind along at several times the speed of sound. And so they've got a good idea that this is going to work, I think.
Yeah. As we've seen, though, with the space shuttle, all it takes is a tiny little crack in a tile to cause a major catastrophe.
Yeah.
I'll never forget that. But I would imagine with a heat shield type of approach like this, the gas, that too could be exposed if one of the vents or whatever it is they use to release the gas fails.
Yes, I guess that's right. There'll always be some sort of failure possibility, and the trick is to reduce those as much as possible.
Indeed. It will be really interesting to see how this develops. It could be one of the big leaps forward in terms of getting spacecraft back into Earth without having to constantly regenerate shields, because that's what happens at the moment. Once a heat shield has been used, you can't use it again. It's the same with the tiles on the space shuttle. you have to replace them after every mission, apparently. This could be a renewable resource, a renewable approach to the whole thing, which obviously would reduce costs ultimately. And it's still very expensive to get up there, send out your payload or whatever, and then get the hardware back to Earth. So it's been a long time coming. I mean, we're coming up on 100 years of space flight, and it's taken 3/4 of that time to come up with a new idea. So fingers crossed that this is actually the answer. And who knows what else they might figure out down the track that could do the job. So I suppose a question that pops to mind, and this is sort of a very dumb question, I suppose. Why can't they just re-enter slowly to avoid the heat? I'm guessing you wouldn't get back in.
You're limited by, the mechanics of spaceflight. So anything in space that's not coming back to Earth is orbiting at nearly 8 kilometers per second. And that's why you need such a big rocket to put things into orbit, because you've got to not only get the height to 200 or 300 kilometers, but also to push it into this high velocity with respect to the Earth's surface. And when you come back, you've somehow got to dump that velocity. You've got to kill it somehow. Now, I do remember when I used to read Dan Dare, the pilot of the future in the Eagle, they used what they called reactor rockets. So you had the spacecraft was in orbit, and then the command that Captain Dan Dare said was blow reactors, and that was forward-firing rockets that slowed the spacecraft down. And that's what they still do. They fire forward-firing rockets to slow the spacecraft down. But unless you've got the same amount of fuel as you use to put it up there, you can't use that forward-firing rocket to gently land it on the planet's surface. You've got to have something else, and that something else is aerobraking, which is using the atmosphere to slow the spacecraft down. And that's traditionally what has been used. It's the only way we have available at the moment until somebody invents something that doesn't need as much fuel to slow you down as it takes you up there.
Well, that time will probably come, but for now, making your spacecraft sweat could be the new approach. And if you are interested in that story, as Fred said, it's at space.com.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, our final story today is a very scary one because we might not be here next week, or maybe it's a billion years. I always get the two mixed up. But on a serious note, some Dutch scientists have come up with a new theory as to when the universe will end, and it is a heck of a lot sooner than we originally thought, if they are right.
Indeed it is. So here are the numbers, okay, because we might as well start with that. We used to think that the universe would die in 10 to the power 1100 years. So that is a 1 with 1100 zeros after it. That's how long we thought it would take to die. The new calculation is it's a mere 10 to the power 78 years. Oops. And that's a 1 followed by 78 zeros. Look, that's one heck of a difference, isn't it? It's a factor of more than 10 different. It's a factor of more than 10 in exponent, which means that it's very much different. It's so yes, the universe has only got really a brief period of 10 to the 78 years to last. But let's cut to the reason why these scientists are making these calculations. They're scientists actually in the Netherlands. And what they've done is they've looked at Hawking radiation. Yep. And that is the trick to this whole calculation. Hawking radiation is, as we know, the radiation that leaks from a black hole, which is a quantum physics effect, because relativity says nothing can come out of a black hole, but quantum mechanics says, well, they can evaporate very, very slowly. And they do. There's all the evidence suggests that Hawking radiation is a real thing. And so what these calculations are about is how long it takes everything in the universe to come to an end by Hawking radiation. And they don't just cover black holes, they cover everything. They cover neutron stars, which are kind of failed black holes. They cover white dwarf stars, which are kind of failed neutron stars. And these all have a Hawking age. And I think actually the original calculation of 10 to the 1100 years was basically coming from just the lifetime of white dwarf stars. But the new calculation have essentially said the decay time for white dwarfs is sooner than we thought. I think actually the white dwarf decay time originally didn't include Hawking radiation. I think it was just how long it takes to cool down to a completely inert object. So the new calculation takes into account the basics of Hawking radiation. They've got some nice other figures as well, because they can work out how long neutron stars take to decay. That's 10 to the power 67 years. They can work out how long the moon will take to evaporate by by Hawking radiation, and how long it will take a human to evaporate. And those figures are respectively, well, they're the same, 10 to the power 90. So you and I, as we sit here, Andrew, we will evaporate in 10 to the power 90 years, which means we actually outlast the universe, because the universe is going to evaporate in 10 to the 78 years. So we're doing well there. How can we outlast the universe? I'm not sure what the answer to that is.
Yeah, well, nothing could. If the universe comes to a grinding halt, that's the end of everything, isn't it? To qualify this, you've got to accept that they're talking about the fading out of everything.
That's correct.
But the universe will still be there. It'll just be dead.
Unless the accelerated expansion of the universe results in the Big Rip, which could come a lot sooner than those evaporation times. Okay. So you're quite right. This is assuming nothing else happens in the universe. The universe is as boring as anything, and things just evaporate by Hawking radiation. That's the numbers that you get.
Yeah, and there was one other thing we left out of that, and that was the evaporation of brown dwarfs, because they're failed Disney actors. Yeah. So got to take that into account too. And that only takes 88 years.
Okay. Very, very good. That's a neat calculation. I think you should write that up for the conversation, Andrew.
It's terrible, Jack. Horrible. Yeah. No, but it is rather fascinating. So do we know, I don't know if you said it, in number of years, what 10 to the 78 actually means for the universe? Yes, just means 1 followed by 78 zeros. It's a long time. Still a long time.
Yeah, and
we should be right to pay the water rates next week then.
That's right. I mean, put it in perspective, the Earth is probably going to get melted within maybe 4 billion years. What's that? 4 times 10 to 9 years. So, that's going to be a much more immediate problem for us than the evaporation of everything by Hawking radiation.
That's assuming humanity has actually survived that long, which is a totally different
we might
argument, theory, whatever you like.
Yeah.
All right. That story available through phys.org, phys.org, if you want to read up on it. It's really, really interesting. And that brings us to the end. Fred, thank you very much.
Pleasure, Andrew, as always, and we'll speak again soon, I'm sure.
We will, and looking forward to it. And don't forget to visit us online at our website and visit the shop while you're there, or just have a look around. And that's at spacenutspodcast.com or spacenuts.io. I would have said thanks to Hugh in the studio, but he couldn't be with us today because he reached the age of 10 to the 78, and that was the end of that. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.